In transceivers, you can either couple the light into a photodiode, or if you're using silicon photonics, you couple into a waveguide of the chip. If you want to find out how it is done, just stick around and we'll check it out. Depicted on this whiteboard, we have a simplistic drawing of a silicon photonics chip. So we have a substrate, then we have a waveguide. Directly coupled to this waveguide is a photodiode and the amplifier. Now the question is, how do we get light into the waveguide? There are several ways to do this. One way is the edge coupling. Means we have a light source here, we have to align it precisely to the waveguide, and this alignment has to be held over all the conditions. But more than that, we also need this edge, and the edge has to be polished, or at least in a surface quality that we can couple in light. Especially for silicon photonics, the question is, isn't there a way which makes it much easier? For example, if we can couple in from the top side or in a larger area. And indeed, there is a way. First of all, let's have a look at this waveguide. By definition, the waveguide has a higher refractive index than the material outside the waveguide. And no matter which angle we choose here, we never meet the guiding conditions for the waveguide. So meaning we cannot get the light in with internal total reflection. But there's a way, the so-called grating coupler. Shown here is a waveguide, and we have the grating on top of the waveguide. And as you can see, the light is hitting the grating, and so the light is guided inside the waveguide. Now the question is, how does such an optical grating work? To explain this, we should first have a look at what happens if a wavefront hits a slit. Depicted here are the wavefronts in a linear propagation, so they are hitting the slit, and behind the slit, these waves are converted into cylindrical propagation, meaning they are running in all different directions. If we now combine several of these slits to an optical grating, we have a little bit of a different situation. Depicted here is the grating, and we are focusing on one direction of propagation, on an angle alpha. The waves behind the grating, they are starting all at the same time at the grating. But if we look at the wavefronts, there's a difference between, a path difference, because they are propagating under an angle. And depending on how big the path difference d is, we have different situations. If d equals 0, lambda, 2 lambda, and so on and so forth, we have constructive interference. Meaning, under this angle, the intensities add up. If d equals lambda half, 3 half lambda, we have destructive interference. Meaning, they are cancelling each other out. If we now take a look at this plot of the intensity, you can see we have constructive, destructive, constructive interference in alternating order. And these orders, 0, 1, 2, and on the negative direction, they are representing the angle. We have prepared a little experiment which you can do at home, because you all have an optical grating, at least you used to have, meaning this CD. And if we now put the focus on this CD, we have diffraction. Here you can see the 0 order. This means this is the direct reflection. We have the first order, the second order, and so on and so forth. You may recognize the 0 order has the highest intensity. And this is not the optimum situation for our silicon photonics chip. But by designing our grating, we can determine which of these orders has the highest energy. And by that, we can put this highest energy in an angle which meets the conditions for total internal reflection. So this means most of the light is coupled to the waveguide. Those grating couplers also have some disadvantages. For example, they are very sensitive to wavelength, to polarization, and they have a principal insertion loss of around about 1 to 3 dB. But this can be okay for the application in a silicon photonics chip. I hope you learned something today. If so, please leave a comment and see you in one of the next videos. Bye bye!